Hello children, welcome back to the channel. As promised in my last video, today we will be taking up certain problems related to moment of inertia. Now, for the first problem, we have been given that there is a uniform rod AB standing on its end A on the ground, and then it's allowed to fall. The length of the rod is given to be L. So, when the rod is allowed to fall and it comes and B hits the ground at some point, right? It will hit the ground at some point. See here. Now, we have to find the velocity or the speed at which the end B will hit the ground. We have to assume that the rod doesn't slip at A, which means that the rod was standing like this and will just fall like this under gravity. So we have to find at what speed the rod is going to hit the ground. To solve this problem, we'll make use of different concepts that we have developed over the last couple of playlists of mine, that is work energy power, laws of motion, and also rotational motion. The link to those videos are given in the description below. You can always refer to them if you need any reference. Okay. So what is happening here is that if the rod is AB rod is allowed to fall about A, so the end B is going to move in a circular path of radius L. Okay, so when it falls and reaches this, what will be the velocity? So it's a case of rotational motion about this particular point. Now, first of all, let's consider, since the rod itself is uniform, so its midpoint here, that is at a height of L by 2. The center of mass will lie here. Okay, so we can consider the entire mass to be considered at this particular point also. So, why it is important is that if we consider this, then we can find that the potential energy of the rod when it was standing would simply be M, if M is the mass of the rod, capital M say, G, and L by 2, where L by 2 is the height of the center of mass. Okay. Now let us consider the second part of it, that is the rotational motion part. Now what will happen is that when the rod rotates and falls here, point B is going to gain kinetic energy at the expense of potential energy, because the center of mass is also going to follow a circle of radius L by 2. So by the time B reaches point at the ground level, the center of mass will also reach the ground level, which means the potential energy will become 0. From conservation of energy, we know that if potential energy becomes 0, then the entire energy has to get converted into kinetic energy. So what we will do is that this is the potential energy, initial potential energy. Now when B reaches here, what is that? Gain in kinetic energy. Gain in kinetic energy, since it's a rotational motion, it will be given by half I omega squared, right? Where I, this moment of inertia of this rod will be about the point of rotation. The axis of rotation will be here, so it will be about point A. Alright, now we come to a place where we need to find the angular velocity and the moment of inertia. Now if you remember in my previous video, I had said that we need to memorize certain values for moments of inertia of certain specific type of objects. One of them was a uniform rod, thin uniform rod, which is the case here. So for a thin uniform rod, moment of inertia about an axis perpendicular to the rod like this and through one end of it, as is the case here. What was it? It was I was equal to, what was it? M L square by 3. That is why it is important. If we do not have this value, we will not be able to solve this. So that's why we needed to memorize those things. We can always derive this, but it will be a little longer process. We can always derive it. Remember that. However, memorizing that will help you a lot. So IA is ml square by 3. Now v is the velocity with which it reaches the ground. Right? This length is equal to the length of the rod. Now we know that for rotational motion v equal to r omega, where r is the radius of the circular path. So if you consider point B whose velocity has to be found, v will be equal to L into omega. That is to say, omega will be equal to v by L, which means kinetic energy that it has gained will be, point B has gained will be half, I will be m L square by 3 multiplied by omega square will be v square by L square. Or we can say this is equal to m v square by 6. This is equation 1 and this is equation 2. So if we now apply conservation of energy, the potential energy lost will be equal to kinetic energy gained. Therefore, 1 and 2, these two equations will give us mgl divided by 2 will be equal to m v square by 6. M's will cancel, this will be 3. Therefore, v square will be 3gl. That is to say, v square will be equal to, v will be equal to square root of 3gl, which is our required velocity. Okay, now the next problem is that a solid cylinder rolls down an inclined plane from a height of h. Okay, the height of the point from which it is released is given by h. What will be its rotational kinetic energy when the cylinder reaches the end of the incline, that is foot of the incline, that is the ground level? We have to find the rotational kinetic energy when the cylinder reaches the ground level. Again, in this case, we will still be using, first we will be using the conservation of energy again. So, first thing first, when the cylinder is at the top, that it hadn't started rolling, right? So, when it was at the top, the potential total energy was potential energy, and the potential energy was equal to mg into h. Okay, when it reaches the ground, the entire energy becomes kinetic. However, the kinetic energy, let's call this point A and this B. So potential energy at A and kinetic energy at B will be, it will have two components. First component is kinetic energy of rotation, and the second component is kinetic energy of translation. Because as it rolls down, it will also acquire certain velocity, linear velocity, and it will reach here with certain velocity v, say. So, kinetic energy of translation will be half m v square, where v is the translation velocity at which it reaches the point B. And also, kinetic energy of rotation will be half I omega square, where omega is the angular velocity with which it reaches the point B. Okay, so this will be equal to half, if we substitute for V, okay, half m, V is equal to r omega whole square, and this will be omega square. Now what is I? If I know the I, then we will be able to use conservation of energy between these two and find an expression for omega. That is our first aim, because we want to find the rotational kinetic energy, which is half I omega square. If I find I first and then we find omega, then we find rotational kinetic energy. So what is I? What is moment of inertia of a solid cylinder about an axis passing through it along its axis? That again from the chart you can find, or you can also derive, but as I said, we need to remember that will be half m r squared. Okay, so if you substitute this value, half m r squared, and so what do we have? 1/4 m r squared omega squared plus half m r squared omega squared. That is to say 3/4 m r squared omega squared. So that is kinetic energy at point B. So conservation of energy will demand that P equal to potential energy at E at the top must be equal to kinetic energy at the bottom. Okay, assuming there is no loss of energy in between. So we must have mgh must be equal to 3/4 m r squared omega squared. M's will cancel, right? So what do we have? Omega squared must be equal to 4gh 4gh by 3 r squared. So we have found an expression for omega squared here. So we need kinetic energy of rotation. Therefore, Kr will be half I omega squared, which is equal to half I, we already know, is half mr squared, and omega squared we have just found 4gh by 3r squared. So r squares will cancel, 2, 2 and 4 will cancel. So what we have? mgh by 3. Therefore, kinetic energy of rotation will be mgh by 3. Okay, so we have found our solution here. And if Kr is this, what will be the kinetic energy of translation? From conservation of energy using this equation, we can easily find translational kinetic energy. K translational will be 2 mgh by 3. Please verify this at home and let me know in the comments. Okay, the next problem, it states that a uniform circular disc of mass m, small m, is set rolling on a smooth horizontal table with uniform linear velocity v. So we have a smooth horizontal table and there is a disc of mass m, and it's set rolling with a velocity v. Linear velocity is given the v. We need to find the total kinetic energy. So the disc is rolling with certain angular velocity and its translational velocity is v, and we are to find its mass is given to be m, and we are to find the total kinetic energy of the body. Now what is the total kinetic energy? Total kinetic energy is kinetic energy of rotation plus kinetic energy of translation, right? Translational and rotational kinetic energy, which are of course half I omega squared plus half m v squared. Now velocity is given to be v and mass is given to be m, so kinetic energy of translation is already found. What we need to do to solve this problem, to find the total kinetic energy, we need to find this term, half I omega squared. Now for a uniform disk rolling about its own axis, rotating about its own axis, I is given by half mr squared. Again, a standard result. We need to remember that. That's why we need to remember the standard results. Or you can always solve it, which is of course tedious and time consuming, which we do not have during exam times. Okay, so this has been found. Now what is omega? Omega will be always v by r, v equal to r omega. So omega is v by r and I is this. So k rotational, which is half I omega squared, will be half into half m r squared, and then omega squared is v squared by r squared. So r squares will cancel, so we have 1 by 4 m v squared. Therefore equation 1 will give us total kinetic energy equals to half I omega squared. We have found it to be 1/4 mv squared. So 1 by 4 mv squared. Sorry, I have taken m, right? Capital M. This should be small m everywhere. So half m v squared. Oh, 1 by 4 mv squared plus half mv squared. That is to say 3 by 4 m v squared. See, the radius of the disk has not been given. We have assumed it to be r. However, it cancelled out, so it doesn't play any role in the finding of the final value of the kinetic energy.